when it comes to precipitation day, I do. Yeah, yeah, you watch yourselves. I'll make it rain on your wedding day. All right. So let's see here. You just turned in homework 3. Oh, I printed off homework 4, but I left it in the engineering office. I was going to actually give you a paper copy of it. Sorry, guys. The PDF is online. I'll bring it in next time because it's not due until Thursday the 21st. And so it's a rare situation where you've actually got sufficient time to work on an assignment. Don't worry, it won't happen again. Yeah, so that's what's on the schedule. We're talking about rainfall, precipitation. Any questions before we move forward? Yesterday I finished grading homeworks 1 and 2, and I would encourage you to look at the solutions that are online for those. In a couple of cases I noticed, for instance, on the time of concentration calculations, a few people didn't convert from hours to minutes. And so, for example, one of the equations was maybe saying the time of concentration would be 0.65, and maybe someone assumed it was minutes, but really it was hours. And so a few minor mistakes like that. But have a look at the solutions and let me know if you have any questions. All right, so last time we were talking about stormwater control. Some BMPs, as they're called, best management practices for trying to slow down the movement of water in its inevitable progression towards the outlet. Whether the outlet is a creek or a big river, what we want to do is when we urbanize areas, we speed up the hydrologic cycle, and we would prefer to have it be slower, because when we slow the hydrologic cycle, there are lower peaks. And then we don't have to make the pipes as big, and it causes less scour, and there's less sediment loss. And so there are real advantages for us to trying to slow down the movement of water. And this diagram is taken from the text, and it's kind of a conceptual figure that shows some of our preferred alternatives for reducing those peak flows. And it makes the delineation between source control efforts and what are considered downstream storage efforts. And what I said in class last time is it's always easier to deal with the stormwater upstream. As soon as the water droplet hits the ground, it's going to be easier to delay a single water droplet than a stream of water. So things that we can do to, for instance, enhance the infiltration is going to have the biggest effect on reducing peak flows downstream. And so if we can promote infiltration, for example, by amending the soil in a detention pond, or instead of having a paved parking area, if we can get away with a grassy parking area. I was up at the Wood County 4-H grounds over the weekend, and they have an enormous parking lot, but it's all grassy because that area is only used a few times per year, and so they don't need the durability of asphalt there, or even gravel. So the things that you can do to try and improve the infiltration of the soil, those are considered local disposal efforts. Inlet control is when we're talking about trying to put a green roof on the building here, or enhancing storage underneath the parking area like they have at the practice facility. These are things where it's going to be more expensive than just changing from asphalt to porous pavers. And there has to be more engineering involved, because you're piping the water from someplace, you're reinforcing a structure to make it strong enough to hold the soil and the added depth of water on a roof. And then finally, the last thing we can do that's source control is when the water actually does pool together, try and time its release. And so we did an Excel example where we looked at the difference between the inflow and the outflow and trying to delay it by having a pool of water that rises in depth and then decreases in depth. And that's the idea behind any of these on-site detentions. So if it's just a small shopping center, it's better to have storage at the shopping center scale than where many different shopping centers and neighborhoods all drain to a single location. Because you'd think that if you have 10 shopping centers and 10 detention ponds, maybe that's somehow less efficient than a single detention pond. drawing water from all of those 10 shopping centers. But it turns out that the total volume needed is less the more of them you have and the closer they are to the origin that the water is being generated, because you're able to slow it down more and reduce the peak. If it's all going to a single big pond, then the total volume has to be larger. And so that's, I guess, what you could think of as a synergistic effect, and it's negatively synergistic. What we would rather have is smaller ponds. All right, so downstream storage is when all of these efforts can't do everything we need, and so we have to provide protection downstream so that we don't have flooding. And so that may be an offline detention, which is a temporary storage vault that we're able to shuttle water to, like the case in Japan that we looked at the video, or inline detention, which are ways of having just what they sometimes will have here in Huntington, for example, is in the overpasses, the underpasses that often get flooded, they have the big vaults there with pumps, and so when it first starts to rain, there's some capacity for storage there, and it's drained automatically, but it's not like the water is pumped into a separate location. It just flows there by gravity. And then finally, having detention at a wastewater treatment plant. So I'll show you a picture of one of those in just a moment. But the main idea, just to summarize, is to reduce the C value, where a high C value means higher runoff because of more impervious areas. What's that sound? Is it draining? Okay, weird. Detaining the stormwater where it occurs and then trying to detain it as quickly as possible rather than allowing it to accumulate. So we looked at that video of porous concrete, and here's kind of a cutaway of what that looks like, where you can see that there is the aggregate, which is covered by cement, but there's no sand inside. And so you have pores that are connected, and that allows the water to flow through it. But if this is in a puddle and it freezes, it's just going to crack this apart very easily. It doesn't have the same strength that ordinary concrete would. Inlet control, where we have storage underneath the parking area, is obviously going to be more expensive because these tanks cost money. You have to be cautious about the bedding that's underneath it to make sure it doesn't become crushed. You have to be cautious about the amount of cover on top of it to distribute the loads. Any engineered solution is just going to be more costly than a solution that's strictly at the surface. Here's inline detention, where they're trying to have an underground canal that's got a lot of capacity, much wider than it would need to be for the ordinary flows, but it's kind of like a very large, shallow channel that the water could accumulate there during a big storm. And then finally, in wastewater treatment, it's common to have what are known as flow equalization basins, especially if you have combined sewers. Because here in Huntington, where we have a combined sewer, on a rainy day like today, if a big surge of water came through the treatment plant, then they would have to release water out of the treatment plant before it was before the pollutants were removed. You know, a wastewater treatment plant depends on bacteria for the most part to remove the pollutants, and the bacteria can't be turned on and off like a pump. They need time to mature and to break down the food that they eat. And so we have to have these big storage tanks at treatment plants to try and act as equilibration and bring the flows towards a more normal mean. All right, so those are some things we can do to prevent cases of flooding. Let me dim the lights a little bit so we can see these pictures. These are all photos of flooding taken here in West Virginia. And ironically, all these photos were collected before the events of last summer. And I could probably do an entire 75-minute lecture just looking at the damage that occurred during the flooding of last summer. And then there was a little bit of flooding this summer. I should grab those pictures of the... I wasn't able to drive to my house. I already told you about this, right? Where I was... there was flooding over the road from both directions, and so I was completely isolated from my home. Now, that was just a temporary inconvenience, not like these people who are suffering real significant damage. Flooding is in the news because of what's happening with the hurricanes down south. In fact, right now my brother's staying with me. He's from Miami, and he and his family drove up here starting on Wednesday. It took them a couple of days because of gasoline shortages and traffic jams, but they got up here, and fortunately their house was unscathed. A friend of his who stayed behind did a video walkthrough, and it looks like, besides a few rain gutters, they didn't suffer any damage, but there's a lot of people who did. So we already know that in a wet environment like West Virginia that flooding is really important, that hydrology, understanding the amounts of water that there's going to be and the timing of it, is crucial information when you have consistent rainfall. But, I got to show you this video of a home on fire while it floods downstream. Maybe you've already seen this. You guys seen this video? All right, I got to pop. Okay, and then this picture was taken, this is the one photo that I got from last year's flooding, just because I'm familiar with Richwood. I've been out there a few times. It's a cute little town, and you know, they suffered a lot of flooding and damage in the cleanup. When we talk about the predicting and preventing flooding, one of the things that flooding causes is direct damage. And so, you know, like water damage to the walls and the carpet, and you know, there's a direct cost of the repairs that have to go into fixing up after a flooding. But the indirect damages of flooding like this is that once an area has been flooded, businesses may decide not to reopen, or companies that were going to maybe relocate to an area will reconsider if they are suddenly reminded of the risks of being in business in a certain place that's prone to flooding. And so there can be a reduction in the tourist traffic that otherwise would have been in an area. And so a lot of the damage that can't be reimbursed sometimes are these indirect costs of flooding, which are even more important to protect against. Hydrology is also important in arid regions, and I bring this up because I've taught over in the Middle East a couple of times, and sometimes it's difficult to convince people that in a place where it'll only rain 3.5 inches per year, as opposed to our 40 inches of rain per year, you know, they think, well, it doesn't rain very often, so rainfall isn't very important. But actually, rainfall is equally important, in some cases even more important. And you can start to get the context clues that actually hydrology is kind of an issue that's on the radar for public planners and engineers over in the Middle East when you see these enormous canals, very, very wide canals coming out of the mountains, and they just go straight into the sea. You can see, obviously, they're expecting some big flows to come down out of the mountains. It's just that they don't happen very often, but when they do, it's a flash flood. Here is one of the largest groundwater recharge reservoirs that's been built in the United Arab Emirates. This is in the Emirate of Dubai. It's out in an area called Hatta, and there's actually quite a lot of agriculture in the Middle East. They're trying to develop more food sufficiency and you know, reduce the need for importing foods outside of the country, and so they try and have as many dams as possible with the goal of getting it back down into the ground, because that's where it's not going to evaporate and the farmers can draw on it for agriculture. Here's a different one. This is a dam that I went out to every couple of weeks 2 years ago when I was on sabbatical. I needed to go out there to take measurements of stream flow. So it was a really beautiful place, and this has happened to be after some wet weather that they had. And unfortunately, in this particular location, the groundwater wasn't being replenished as well as it would have, because there was a bunch of fine sediments at the bottom of where all of the water accumulates. They weren't maintaining this recharge dam like they maybe should have, because if you think about the hydraulic conductivity of very fine sand and silt, it has a very low hydraulic conductivity. The water can't move through fine voids very easily. So a solution to that is to occasionally scrape the top layer of very fine soil away, and you know, you can haul it off and use it for agriculture, or sometimes they'll drill they'll drill boreholes down into the ground. It's kind of like the opposite of a withdrawal well. It can be an injection well. And through screens and coarse gravel around the outside edge of the borehole, then promote infiltration. They hadn't done that here yet. Maybe someday they will, but it's a beautiful structure. So in arid areas where they're developing very quickly, the populations are growing rapidly, it's pretty common to have high-rises built without a lot of thought given to what may happen when it rains. And so people are parking on sandy areas, and normally sand can absorb a fair amount of water, but when it rains really quickly, the water levels rise fast, and then cars go under water, and you know, this Mercedes, which probably was a really nice car, isn't going to start anymore. It's ruined. They still have plastic on the seats, but yeah, keep the seats nice, but unfortunately they parked in a low-lying area, and so that vehicle is finished. These are some photos I took as I was driving around during a rainstorm many years ago in Sharjah, which is the emirate next to Dubai. The taxis, they would have been better off with boats that day. This guy didn't have a raincoat, but he did have a plastic garbage bag. I didn't happen to notice that he had a breathing hole. I hope he didn't suffocate out there, but he stayed dry. So they have impromptu water removal because there aren't, in some of the roads, there aren't storm drains, or there aren't, like, not only is there not a separate stormwater collection network, but they don't allow the stormwater to get into the sanitary sewer. And so instead what they'll do is have these big trucks that will pump water from critical like underpasses or intersections, and then they have to go out to the desert and then spray the water out in the desert. And it's really dangerous work. This one was in an accident because these trucks are kind of lined up and the visibility is bad and it's raining and the road is slippery, and so it's not really efficient to pump the water out one truckload at a time. It's far more efficient to have the stormwater sewer when possible. When these large puddles accumulate on the edge of a road, obviously this is a transportation hazard because any car that comes driving down the road and just two of its wheels are going to be in that puddle, it will draw the car to the right. And so stagnant ponds of water can cause accidents in cars, and also this is a prime mosquito breeding environment. Here's just some pictures of conditions on campus where I was working when it would rain. They have these speed bumps, really large speed bumps, to try and encourage people to slow down a little bit. And they've got problems with speeding on campus, but these speed bumps also act as kind of like little dams or broad-crested weirs, so the water will get a foot, 18 inches deep as it gets up against these big speed bumps on campus. Another thing that was always a little bit tricky for me is when I was over there, I wouldn't dress as casually as I do now. Most days I'd wear a tie and like dress shoes, and the dress shoes were really slippery. And so this is polished granite, and you're wearing like slippery dress shoes on polished granite, and then it starts raining, and you know, it's like walking around on an ice skating rink. It's really slippery. So the point is that hydrology is important everywhere. In arid climates, in wet climates, it's important everywhere. And where hydrology is looking at the amount and distribution of rainfall at the surface. And so distribution can mean two things. It can mean temporal distribution, so you know, how quickly it arrives at certain locations, and it can also mean spatial distribution, which is how the amounts vary in space. Now, in the subsurface, we won't spend a lot of time this semester talking about subsurface hydrology. There are entire courses that just are strictly focused on the movement of groundwater underground. We'll do a little bit on wells towards the end of the semester, but we're focusing mostly on surface hydrology. And there's an important link between hydrology and hydraulic engineering. In hydrology, what we're trying to do is develop an understanding of the the runoff amounts so that then the hydraulic engineer can size things like in the case of pipe flow, the flow of water from a treatment plant to homes. So closed conduit flow using the Darcy-Weisbach equation or Hazen-Williams approach. And then an open channel flow, the hydraulic engineer is usually using Manning's equation to predict the depth of flow and the width of a required canal in order to convey this runoff out to the ocean or to a stream where it's going to be received. So the water cycle is at the heart of this understanding and the analysis that happens to give the answer to the hydraulic engineers of what is the Q. The water cycle that we're going to be looking at is how does the water get from the ocean up into the air and then down over the surface. And this cycle, you can get an idea from the size of these arrows, the relative amounts. And the next slide also has some relative quantities listed. But some of the most important factors that we're going to be studying through homework assignments are the precipitation amounts and the websites that are out there that help us to find for a certain location of interest how much rainfall we can expect over what time period. Not just the return period, meaning like a 5-year storm or a 10-year storm, but also the short duration that's interesting to us because of the time of concentration. We're also later in the semester going to be doing some homework assignments related to the evaporation of water, not only from open surfaces of water, but also the evaporation from plants, which we call evapotranspiration when the plants exhale moisture and it gets up into the atmosphere. And then of course a big part of what we'll do is the movement of water over the surface, and so trying to predict the temporal distribution of how quickly it arrives at a certain location. Okay, so this figure is showing relative quantities, and these numbers really don't have any units. It's just relative to the amount of precipitation that happens on land. If we say that that's 100, based on the area of the ocean relative to the area of the earth, there are 424 units of water evaporation from the ocean, and most of that precipitation occurs on the ocean rather than onto the land surface. And so you can see that of that 100 units of precipitation, much of it will evaporate back up into the atmosphere rather than actually running off and making its way back to the ocean. 38% of what has precipitated will make its way to the ocean compared to the majority of it, which evaporates and gets back up into the atmosphere. This is an interesting figure which can give you an idea of the scope of where the water is, like where it's located and how much of it's actually usable for humans. Starting on the left side of this figure, it says that if we think about all of the water on the earth, the majority of it is in the oceans. And because it's salty, it's really not cost effective for us to use in most cases. You know, there are places where desalination is an important source of water, but it's fairly expensive. It costs about, roughly speaking, 50 cents per cubic meter of water to produce it by either thermal distillation or reverse osmosis or membranes. So it's pretty expensive and it requires a lot of electricity, and so then there's greenhouse gas emissions from producing water from ocean sources. But a tiny little fraction of the Earth's water, if you look, 2.5% of the total global water is fresh. But we can't use the entirety of that 2.5% because it's in the wrong place. The water that's in glaciers and ice caps, so the water in Greenland or the water at Antarctica, that's not really useful to us because people don't, not very many people, live in those locations. What we usually rely on is surface water, meaning the water in lakes and streams, and groundwater. And of those, you'll notice that groundwater by far exceeds the amount of water that's available for surface water. But then again, the problem with groundwater is that a lot of groundwater is too deep for us to pump it out. And also a lot of groundwater is just water that's bound to the soil very tightly. We can only use groundwater when the voids are fully saturated. That's when we're able to pump water out of the soil. So even if there's soil moisture, it's not until the soil moisture is completely saturated that we can extract it with a pump. So we're actually really fortunate to live next to a big river that has essentially an unlimited supply. I mean, I've never seen the Ohio River run dry before. I don't know that it ever has. Even in the worst drought that we've had here in the east, I think the Ohio River always has water available. So we're kind of spoiled that this tiny little sliver of the Earth's water is so plentiful available where we are. You can see that a lot of the water that's even considered as surface water, but therefore should be usable, is ice and snow, and so then we have to melt that in order to use it. So just drives home the point that water is scarce, and we have this love-hate relationship with it in hydrology. We view it as a resource, but then it's also a nuisance that we have to dispose of. And it all depends on timing. You know, timing is everything, whether the water is something that's going to cause damage to infrastructure, or whether it's something that we can use and grow crops out of, or maybe generate electricity. So timing is important. This is an important point for us to kind of introduce the idea of a watershed. Now, watershed is a little bit of an ambiguous term because there is no way to say where a watershed ends. Those divisions are sometimes a little bit arbitrary. I'll show you what I mean in just a minute. But there's a variety of words that are used to describe the same concept: drainage basin, catchment, watershed. Here in West Virginia, we call them hollers. In the UAE, they call them wadis. So those are some local words for those. Let me see if I can just briefly show you a watershed that I'm familiar with. Give me just a moment here to pull it up on my computer. And it's free now too, the pro version. I used to have a license for the pro version, and now they're just giving it away for free. It allows you to, one of the interesting features, it allows you to pivot downward, and if you rotate around, you can get a feeling for the three-dimensional. Now this remote connection is a little bit glitchy, but all right, here we go. You can see that there's a ridge line, and as I pivot around, the location of that ridge line becomes a little bit more obvious. But you can think of this as kind of like a bucket that the rainfall is going to fall into this trough and make its way to the lower elevation. And so it's through rotating around that you get an idea of where that ridge line is. You could draw the ridge line, you could trace over it, but right here is a road. And so all of the water that falls in that catchment is either going to infiltrate, evaporate, or flow over the surface and therefore under this road. There's going to be a culvert at the crossing of that stream and the road. And so we could say that this is a watershed. But this watershed exists in a larger watershed. And so if I zoomed out more, then there's going to be many of these smaller watersheds that feed into a larger stream. And you can see here is a stream. And so the point is, I could put a pin on the map any place, and then I could delineate the area upstream that's contributing to that watershed. So, for example, if I drop the pin right here, then only this area is going to be contributing to the watershed at this location. But then if I drop the pin here, then the watershed area that's contributing to flows is much larger. And so that's a nested hierarchy that the idea of an outlet becomes a little bit relative on the area of interest. And so here's a figure that illustrates that nested hierarchy, that at the small scale you may have a watershed that's just your backyard, but what you do in that watershed contributes to the flows downstream. And so when a business puts in a big warehouse and a large parking lot and the roads are widened to go to that business, then it's not just inside of a small watershed that the effects of that disturbance are felt, but it's everywhere downstream because one watershed is nested inside of another. The amount of runoff we see depends on not only the size of the watershed and the contributing area, but also it depends on the land use, like what's actually at the surface. If it's asphalt pavement, there's going to be more runoff and less infiltration than if we have a natural forest litter that not only is allowing more infiltration, but it's slowing down the movement of flow because there's more roughness there. The soil type is an important factor, and clay soils, like are common here in West Virginia, don't allow as much infiltration as sandy soils that they have in other places. And that's part of the reason why we have flooding so often here. In the hydrology that we're going to do, some of the models we create, there are 4 letters of soil classifications, A through D, where D soils have more clays or plastic conditions and they don't allow as much infiltration as soil class A, which is more sandy soils. And around here, most of the soils are either C or D. It's very uncommon to have soils that infiltrate water nicely. The terrain conditions have a big impact because if you think about how steep the terrain is, that's going to affect the speed that the water can move over the surface. And really steep watersheds have what are described as flashy conditions compared to watersheds that have a milder ground slope. And again, that's kind of a strike against us here in West Virginia. We have flashy conditions because the watersheds are very steep compared to some other areas that are experiencing slower moving water over the surface of the ground. And of course, the amount of runoff you get also depends on the rainfall intensity. You know, over time, when does it occur? And that varies from place to place. The rainfall patterns that they get in Seattle are really different from the rainfall patterns that we get here in West Virginia. And the reason it rains in Seattle or other coastal areas is different from the reason it rains here. Rain forms for different reasons. We're going to talk about the scientific theory and the fundamentals of what causes rainfall today. And part of what causes precipitation is the movement of air. And air movement across the globe occurs for a variety of reasons. It's partly that the Earth is rotating, it's partly because there are temperature differences in the atmosphere, but then it's also that the Earth is warmer at the center near the equator than it is at the poles. And so that difference in temperature at the equatorial areas, this figure is showing that the air is generally speaking rising, and at the poles, because it's so cold at the poles, the air is falling. And so that sets up a circulation that's called Hadley circulation. And so this is one of the terms that I hope you'd be able to describe in a short answer, like on an exam scenario or a quiz. And you know, a figure showing the rising air at the equator and the falling air at the poles. And so this is in 3 dimensions. So you have to think about it's an entire blanket of air that generally speaking is going down until it reaches the equator, then it goes up. But that's not the only air circulation pattern that exists. There's also the effect of the rotation. And so if you combine Hadley circulation with the fact that the Earth is rotating, then we have the Coriolis force, which means that at different latitudes there are different typical wind directions. And this little animation is kind of showing that as you have rotation and you have something that's moving from the center towards the outside edge, that it's actually having more of a curved path. And so the curved path of the winds is because the Earth is rotating circularly, and the Hadley circulation is driving it from warm towards cool. And so here in North America, we expect that the weather is coming from the west towards the east. We just take it for granted that, you know, if it's raining in Indiana this morning, then it will be raining here in West Virginia by the evening. We always look to the west to find out what our weather is going to be like. It's kind of strange to think that in other places they look to the east to find out what the weather is going to be. In Africa or down in Central America. And there is a dividing line between the westerlies and the trade winds. Here's another figure in just a moment that shows that dividing line. And if you think about the path that the recent Hurricane Irma took, so its path it's from out in the Atlantic Ocean and it approaches the Caribbean, and then it gets pushed up towards North America. And so if you think about those typical air directions, it kind of makes sense with the path that the hurricane was taking, that it's the air that is being pushed down and the rotation where the globe is turning, but the air is turning less than the globe is. So there's this dividing line where the hurricane kind of is coming towards a westerly direction, and then it gets pushed up into the northern latitudes and starts heading up the coast. So it's kind of interesting to think about just how the general circulation of the atmosphere shapes the specifics. Another thing that's kind of interesting is that there's no such thing as just localized precipitation. The evaporation that occurs in a single location is going to have global consequences. And this figure, what it's showing is they were able to measure the evaporation in a small section of South America and then track over time where that evaporated moisture actually ended up. And so it gets broadly dispersed, and then the evaporation that occurs at this location is going to be broadly dispersed, and it doesn't take too many jumps between evaporation in any single location having a worldwide effect. And that's part of the reason why we get concerned when there's a nuclear meltdown in Ukraine, is because we know that that air is going to be distributed everywhere. And if there's polluted water in maybe Sweden or the UK because of acid rain, that acidic rain is going to acidify other locations besides just the specific first place that it fell. And here's another diagram showing they repeated the same model in Asia, and that precipitation, that the evaporation that occurred in Thailand and Vietnam ended up precipitating as far away as Georgia, South Carolina, West Virginia. So it's a global effect. All right, so let's talk about the physics of why it rains. This is something that I need you to be able to describe in your own words. And so I'm going to explain it to you today. You need to read through your textbook, the commentary it gives on the forces that shape precipitation. But it begins when you think about air that is relatively warm and moist. When it begins to cool, the relative humidity is going to be increasing. And so air that is cool can't hold as much moisture. And that's when you have a glass of ice water. If you take it outside on a humid day, it starts to sweat. And it's not that water is making its way from inside the glass to the outside. It's that you have something cold and you're taking it into a warm environment with lots of moisture in the air. And so the air that's in the immediate vicinity of the cool glass can't hold as much moisture because the air itself becomes cool. And so the moisture that was in the air kind of precipitates out onto the cool surface of the glass. And so if you extrapolate that out more broadly, you think about air that is becoming cooler can't hold as much moisture because there's a solubility for moisture in air. And you probably remember ideas of chemical solubility, you know, the idea of how much table salt can you dissolve in water. And water that is warm can hold more salt. It can dissolve more salt. And so you have, I hope, in the past thought about the idea of the temperature dependence of solubility. And air can hold moisture, but not as much as it cools. And so when air rises through the atmosphere, it cools off. And so one of the important factors is just the air that is cooling off, the relative humidity is increasing until it reaches saturation. And so precipitation is caused when air is somehow forced to rise, and then that cooling process begins. The chain reaction of air that was moist and warm became cool and even higher humidity until it can't hold any more precipitation. And that process occurs in the atmosphere where there's lots of particles floating around, dust particles, fine salt particles from the ocean. There are these really small nucleation sites that the precipitation occurs onto. And so I was talking about a glass of water, and you can think of these as some surface that the moisture is accumulating on until eventually there's so much moisture in a particle that it can't be suspended in the atmosphere anymore. You know, just normal gusts of wind and the movement of the air can suspend relatively fine particles. Clouds can be floating through the air, but when there's a collision of those particles that they accumulate into relatively coarse sizes, then they'll start to fall downward. The droplets are growing, and then more water comes in to continue the process. There's always more evaporation or more lifting that occurs. And here's a figure that is talking about the idea of the adiabatic cooling. And in fluid mechanics last year, we briefly talked about this idea that if you have a balloon and the balloon is rising up through the atmosphere, it's going to be expanding because there's less pressure at higher elevations. And so a given volume of air is going to occupy more space as it rises upwards, and as it goes through that process, it begins to cool. And the general trend is on average 10 degrees Celsius for every 1,000 meters of elevation. So that's the dry adiabatic lapse rate, is about a degree for every 100 meters of elevation that you go up. It's cooled. So the trend here is as air rises, it cools, and then the relative humidity increases because the solubility of water decreases as the air cools. So what causes the air to rise? The three main factors we're going to talk about is convergence, orography, and convection. And so just as you'll need to be able to describe why it rains and the idea of condensation nuclei and cooling and relative humidity, you're also going to need to be able to describe each one of these three causes of uplift separately. So the dry adiabatic lapse rate is about a degree per 100 meters of elevation. When the air is fully saturated with moisture, it doesn't cool as quickly. And so this lapse rate for saturated air is 6.5 degrees Celsius per kilometer. All right, so here's the first kind of cooling that we're going to be thinking about is when you have fronts that are encountering one another. If you have a cold front that's pushing into a warm air mass, then that's going to cause two different kinds of storms actually. Convergence is the is what we're talking about here, where two different pressure zones are interacting with each other. Normally the high pressure cold air is encountering the lower pressure warm air, but there are two fronts here. This A to B line, this dashed line, if we look at a cross-sectional view of this AB, that's what this figure is. And so what it's showing is that As the cold air approaches the warm air, it's a very abrupt transition. You have a big mass of cold air that is going to be closer to the ground because it's more dense. And it's approaching the warm air, which is less dense. And so the warm air is forced to rise very quickly as the cold front approaches. And those cause these really abrupt and like vigorous thunderstorms that are, a lot of high intensity rainfall from an approaching cold front. But when you have a warm front that's forced to rise up over an existing cool zone, then that's a far more gradual transition where here you can see the warm air is intruding over the cool air, but since it's forced to rise as it intrudes, then the temperature changes more slowly. And so it's saying here a day-long drizzle is common when you have the warm front approaching a cool front. But either one of these we can think of as frontal lifting, convergence, where two different pressure zones are converging on one another. So that's the first of the reasons why does it rain? It's because the air is rising, and as it rises it cools, and then the moisture has to come out of solution with the air, and it has to precipitate down onto the ground. Any questions so far? All right. Here's a picture of an island. What do you think's going on in this picture? We've got some green, we've got some brown. What's that? Rain shadow. Rain shadow? Explain more.
Like how it's, the air has to go up with rains on one side of the mountain or ridge, but the other side doesn't get much.
Exactly. Very good. We call that orography, where there's some sort of a physical obstacle that the wind is coming and an air mass is forced to rise over the obstacle. As it rises, it cools. As it cools, the relative humidity increases, and the relative humidity is going up until it can't go up anymore. It's 100% humidity, and so any additional cooling is going to force the precipitation of moisture onto the ground. And so once the cloud gets to the top, then it's not rising anymore. And so we don't see as much precipitation on the leeward side of the mountain. It's dry on the back, and that's why in this picture we saw one side of the mountain is very green and one side of it's very brown. Here's a figure that illustrates that on the island of Oahu. And one side of the island of Oahu has lots of rainfall. You're seeing like 5,000 millimeters per year. That's a lot of water. And then the other side of the island has only 10% of that on the leeward side. So windward is the side that first encounters the wind. The clouds are rising. All the moisture is dumped on this side where typically the wind is coming from this direction. And then it's much drier on the opposite side because there wasn't any lifting. The third kind of lifting that causes precipitation, which we're going to talk about, is convective lifting. And this is the dreaded afternoon thunderstorm. If you've ever had to fly through Chicago during the summer, a lot of flights are delayed in the afternoon because the ground surface gets heated over the course of the day with the sun shining down on it. And so the solar radiation is heating up the surface of the air, of the surface of the ground, which also heats up the air that's adjacent to it. And so all of that rising air, as it goes up, it kind of forms what looks like a mushroom cloud. And as you're driving around, sometimes it can look like there was a nuclear explosion almost, but really what it is it's just the air that's rising is increasing its humidity until the droplets are increasing to grow, increasingly getting larger, and they're colliding with one another, and the droplets are getting bigger until they fall down. So that's the idea of convective lifting. Here's just a figure again that's showing the lapse rate, the adiabatic lapse rate, and how condensation occurs at a certain altitude because the humidity is high enough, and then the precipitation occurs when The droplets are large enough to overcome the supportive interactions that it's had with the air before that. All right, so those are the three kinds of forces that cause lifting of the air, which leads to precipitation. And if we zoom in on what's going on inside of the cloud, the process of these condensation nuclei, which may be dust or salt particles, which initially have some condensation from moisture just dissolving onto it from the air, and they bounce together, and there's lots of collisions and coalescence, and then finally precipitation. What we're interested in most of the time is rainfall, because although snow, hail, and sleet can cause a lot of problems with slippery roads, they don't cause as much problems with flooding as rainfall does, with one exception. And that is when you've got a lot of snow on the ground and then it heats up quickly. And that, of course, can cause a lot of flooding. But usually the fastest of these precipitation types is rainfall. That's going to cause the flooding that we're most interested in and the limiting factor for sizing pipes. Part of what is interesting about these droplets is that initially they have a negative charge, and you probably remember from soil mechanics that clay particles, for example, are negatively charged, and it's just that when you have a very small particle with a negative charge and all of them have that same negative charge, they are repulsive, and so they don't necessarily bump into each other naturally until the droplets get big enough that the collisions are forcing it to aggregate. Here is a map of our local area. You can see Charleston is on the map. Here's the Charleston Airport. Here is Huntington and the Tri-State Airport. This is a figure that's showing where we've got precipitation gauges in the region, where we're actually measuring rainfall. And so if we were going to do a project in Milton, here's Milton on the map, you'll notice that there are no rain gauges in Milton. So what do you think we do about that? If we wanted to estimate how much runoff is going to come from a watershed in Milton, but there's no actual long-term rain gauges in the area. Okay. Find where it leads to? Yeah. So, we can extrapolate based on, surrounding gauges. In the short term, maybe there would be, and this is actually, I've studied this, at the airport, you may have a big storm one day that particular storm doesn't make its way to Milton. But over the long term, over 5 years, 10 years, there's about the same precipitation as you have in one place as another. And so what we can do is develop curves that describe the rainfall patterns in one location and use them in another that has similar topography, same elevation, same proximity to an ocean, for example. Because the real problem is there's just not that many gauges that have been operating for a really long time. This figure, which is taken from the text, is kind of interesting, and what it shows is that we've got thousands of gauges in the country that have been operating for between 10 and 50 years. But if you want to know what does the 100-year storm look like, how much, if you have 100 years, what's the worst of them that's going to happen, the worst storm that's going to happen over a period of 100 years, there are far fewer gauges that have been operating for 100 years or more in the country. This is a logarithmic scale here. So it's saying that we've only got about 100 gauges in the United States that have been operating continuously for 110 years or more. And so there's a lot of statistical extrapolation and massaging of the data that occurs in order to develop estimates of how much precipitation may happen in a given area. I've already introduced the term of hydrograph, and that is a graph that's showing the rainfall intensity or depth over time. And so here it's broken up into blocks of 1 hour. And you can see that they're measuring the intensity in 1 hour blocks during a storm. We can also graph that precipitation amount on a cumulative basis. And this figure is showing for different storms how much rainfall accumulated during a period from 0 minutes to 420 minutes. So the storm of January 8th, you can see there was a period that it was very intense. The steeper this line is, that's higher intensity. As this line is relatively shallow, that means that the rate of precipitation is lower. So here is that storm of January 8th, and here's that storm again, January 8th. And so you can see that this is when the precipitation rate was lower, from hours 4 to 6. It looks like there's some more data here in this figure than is being graphed in the rainfall hydrograph. This is probably, they've done some averaging, because we wouldn't be able to get something with this many minor variations in it from just this blocky data. You'll see a lot of different creative ways to display precipitation data. This figure, it seems like the point of this figure is to compare storms. You know, to say that on January 8th, not only was there a larger amount, but there were higher intensities that were observed on January 8th than on August 22nd. And these aren't necessarily in chronological order either. It goes from January to August to June. So I think the point of this figure is just to illustrate the seasonal variability of storm in a certain location in the Kickapoo Station. That showing the summer storms are relatively mild, not much precipitation during the summer, really low intensity over time. You've already seen some IDF curves from an earlier homework assignment. The IDF stands for intensity, duration, frequency. And all three of those are displayed on a figure like this. The intensity is on the left vertical axis. In this case, it's displaying the rainfall intensity in terms of inches per hour, and it's a logarithmic scale. The duration of the storm is on the horizontal axis down at the bottom, and then the frequency is referring to the return period. It's the average amount of time between storms of a given size. So just take, for instance, a storm that has a 1-hour duration. If we want to see a storm of that size every 2 years, then it's going to have an intensity of about 1 inch per hour. But if it's a storm that comes around every 5 years, the intensity is up to close to 1.5 inches per hour. And so the less frequently a storm is coming around, the average return period between storms, then the intensity is going to be higher. But then as the duration gets longer, then the intensity goes down. And that's because you can't have a really high intensity precipitation event that is sustainable for a long period because of the clouds. You think about how tall the clouds would have to be and the vertical distance over which the precipitation is coming from. It's just the clouds are always moving. You'd have to have a really high amount of humidity that is coming out of the atmosphere all at once to sustain high intensities, and that just physically isn't possible over the long term. We are going to just look at conceptually how intensity, duration, frequency curves are calculated. And we'll get into more about this in the next class period where we actually download some of the data from online. And so if you'd bring your computer to class next time, that would be useful, because we're actually going to go to some of the websites and take a look at some of the precipitation data. But just broadly speaking, the way it works, the way a figure like this is prepared is through a lot of extrapolation. Like, we don't have a site where we have observed every single storm duration, and so like this curve isn't a plot of lots of individual data points. It's kind of like a statistical extrapolation. And so the real underlying data that you'd have, let me show you an example of like some real data. Let's say that you measured storms for 32 years, and we'll go back to the previous slide in just a minute. You measured storm for 32 years, and you measured it in 5-minute intervals. So every 5 minutes you were looking at the amount of rainfall that had accumulated. So what you could do is you could sort that list, and so that you'd have the highest intensity at the top and then the second highest intensity in the row after that. And so you'd put it in order of decreasing amount or decreasing intensity. And what you would do from that 32 years of data is you can use this Weibull equation to calculate the probability or the return period. And so in our case, if we had 32 years of data, then the row at the top has a return period of 33 years. Just the way that it works is you add 1 and then divide it by the rank order. And so this first return period, the first storm that you would observe over a 32-year period is the 33-year storm. And the next one, your M has increased. M is now 2 for the second row. 33 is still the same in the numerator, but now we've got 33 divided by 2, and so now this row represents the 16.5-year storm. And the row beneath it is the 11-year storm, and so on. And if we wanted to know then what does the 20-year storm data look like, then it's going to be a linear interpolation between the results here and the results there, according to the same kind of linear interpolation that you've always done. So you calculate the t-value, and then this is all actual data to begin with, but then we're going to extrapolate between it. So if we followed that approach, just kind of think about your averaging between these two data points. For the 5-minute duration storm, it's going to be somewhere between 12.1 and 11.0 for the rainfall depth. It's closer to the 11.0 because here, this is the 20-year storm. 20 is closer to 16.5 than to 33. So let me just draw a little figure here to illustrate the linear interpolation. We would have, for our return period of 33 years, we had the amount was 12.1. Down here for 16.5, the amount was 11.0. And so we've got a data point at each of those that we draw a line between, and then if we wanted to know what is the rainfall amount at 20 years, and we would just go over and then back down again, and then from that is why it's saying 11.2. It's just the process of linear interpolation. So we find the slope of the line and multiply it by the amount of additional years beyond 16.5 to get up to 20 years, and then add it to the original baseline of 11, which is the precipitation depth. All right. So if you'll bring your computer to class next time, we're going to go through a couple of different websites that just focus exclusively on precipitation amounts and look at how you can get some rainfall data to finish the next assignment. So I'm sorry I didn't bring those into class today, but if you want to go to MU Online, the next assignment is there. You can start looking at it. I give you a couple of hints about which table and figures to use. You could actually start taking a look on the first problems of that assignment, because it goes along with just a couple of figures in the textbook. Let's see, here we go. Precipitation. So there are a couple of book problems which you could begin looking at now, and we'll talk more in depth on Thursday on what to do with that. But then the part 2 and the part 3 probably won't make any sense until after our lecture on Thursday. But I would encourage you to get an initial look at these problems with part 1. All right, so that's it for today. I will see you in class on Thursday.